Thank you for having me. Good morning, good day, and good afternoon to everyone.
Yeah, good afternoon here. Thanks.
How much time do I have? Is it 20 minutes plus questions, or is it 25 minutes, or what do you have in mind?
25 minutes. There might be questions, but we can answer questions during the panel discussion later. Yeah.
Okay,
we have
so
25
I
minutes.
go
if you want.
ahead
Yeah.
and you stop me when I'm going overboard. So I am sharing the full screen of the PowerPoint. That's at least the goal I have. And this should be this one. Are you seeing myself with a lunar brick?
Good, we got you.
Okay, thank you very much. So my part of this session will address both things we learn on the space station and things we learned not from, but for the moon. I will touch upon a little bit some of the ideas that connect everything we do, also certainly with other planetary bodies. And I'm very much looking forward to the discussion and information exchange. So from basic science to technology, I hold two positions. One is a university professorship in theoretical physics, actually, and I am a group leader at the German Aerospace Institute, not the funding agency DLR. So I'm spending money, I'm not giving it away. Hope to spend it wisely. If we speak of space resources, I've been part of the recently completed gap analysis study within the ISAC-G. I think that covers all the nations, at least the ones present in this panel. And the contribution we from our side are planning or targeting to do is not from the application, but from the side of the basic mechanisms. Going back to Ms. Grab, you can address basic regolith problems on many bodies if you are not only targeting a specific site on the moon. So that's sort of the spirit. Gravity effects, many things in process engineering. And we had the privilege of checking out many gravity effects and developing new diagnostics on and for the space station, and also for sound rockets, parabolic flights, and rock towers on ground. And we certainly try to do good numerical modeling for processes and other stuff based on that and as preparation for such missions. I'm totally happy to pass on my presentation as PDF later on. That's where you should then be able to directly click on the links and have the references to the things I'm talking about. So what do we try to gain from that? So we try to have a basic understanding for, say, building materials and mitigation techniques such as dust mitigation. The picture I show here is arguably one of the first drawings of such kind, where we have the basic engineering behind it. So with current technology on Earth, how to sinter and agglomerate particles from lunar regolith simulant, you can build what I show. So this is not an artist rendering, it's not an architect, this is civil engineering, and those buildings can be built by solar technology, certainly not mission ready, but this is a technical slide, if you like, except for the astronaut, and not a dream. How would some basic information be relevant? So here is my appeal to asteroid. So one of our techniques I show briefly later is sort of stress birefringence. We have others. That is done by replacing actual particles by polymer particles, and then you can see the stresses, which allows you to assess specifically if you have low or even zero gravity, what such a simulated, and it's arguably far away simulated physical simulant is doing if you change gravity. And for that, you can check and cross-check processes that you may model numerically for the preparation of a mission. And one of the things that on the other route can come out is that you may be able, on the label of asteroid defense, to use some of the newly discovered mechanisms in granular media to change to much smarter ways to destroy, deflect, or do other things to asteroids than the admittedly very brutal ways like exploding or deflecting it. May it suffice, again, I give you the links here. If you have mixtures of grains, you may, by virtue of only changing the density very slightly, that could also be a pressure effect, you may very slightly change a small parameter. And if you're crossing that line, if you see my cursor, so this additional line in the jamming diagram from the statistical community increases the mechanical yield stress, for example, by a factor of 1,000. And it is this control of granular media that may come in handy when you have an asteroid approaching Earth, which all of us wish not to happen anytime soon. So may that serve as sort of an introduction or outline. Here I report something fundamental we discussed in the Isaac-G gap analysis. So this is admittedly targeted primarily to the moon because that's the next possible target. It also has some Martian, but only few appeals to asteroid things. And I clearly see that more overlap between those communities would be clearly beneficial also to the long-term business models for both industry and also in science. So if you want to do mining, beneficiation, handling of raw materials as a prerequisite, if you want to do it more scientifically, doing calculation comes in handy. You can either do better calculations or you have novel diagnostics that allow you to do in situ, or as the industry people call it, online or inline measurements. And both of those can also be funded by very big kinds of funding budgets, because this is also what industry wants. They want to do numerical predictions of their models. Digital twins is a keyword, and certainly novel diagnostics where you cannot predict are also very much appreciated by industry, even on ground for mining and even for granular handling. You want to certainly better predict things in an unknown environment. You're not going to Mars and shovel in kilograms of sand to do a shear test at home. We want to go beyond physical simulants. You want to understand regolith well enough that you go different places on the moon, not by preparing different regolith simulants, but by simply changing parameters in your simulation. For doing something, the energy source will most of the time be the sun. It's the most reliable one. And there's always granular soil. So you want to understand both well enough and in their interactions to be able to do those many things that I have here on the right. And different from a top-down approach, when you get money as a company to be a contractor for building a drill on whatever planetary surface, we would do a bottom-up approach that is then, in a sense, flexible to specify down to individual bodies. This is a quick overview of our microgravity research. So we go on the space station, other platforms to study granular gases. You do video monitoring, you can look through, you learn about basic laws. Here, less visible, the installment on the International Space Station. What I have here as a green illuminated experiment doing diffusing wave spectroscopy or similar scattering methods on dense but agitated granular media. And over here, I'm showing a latest development where we are applying sound measurements on soils that are basically granular matter in low and microgravity. And if I come to it, I can explain also here that rocket-looking thing here, that is a concrete experiment for the space station that will happen later this month. In addition to the space station, I told it we also do sounding rocket experiments. So one of the experiments you see here is sounding rocket module. And we happily, gracefully have the assistance of all those astronauts I show here. Executive summary of granular or regolith matter in microgravity could be the following, and I try to illustrate that here from the hourglass. If you turn the hourglass upside down, what I have here too, the upper part is flowing downwards, that I call a granular fluid. When it's falling down, I call it a granular gas. And once it has reached the bottom, I can still look at avalanches and pressure, and this I call a granular solid. I show on the left-hand column the laser measurement. You see those speckle interferences that can be used as a diagnostics. In microgravity, grains are typically at lower gravity much more isotropic, and you have larger fluctuations in their operations. Granular gases are sedimenting not at all in zero gravity and much slower if you have non-zero but low gravity. And you have much more isotropic distributions in both spatial positions and velocity. And even, I mentioned earlier, the stress birefringence. You see here, if I push on granular soil, the stress distribution is definitely non-trivial. And if you do that in lower gravity, you have lesser gradients, you have an evolution of the configurations, and that all comes into play, I would assume, also in handling things on asteroid body, definitely on lunar and in microgravity. Also, there's different ways of building materials. We have here on the left another experiment where pouches, in that sense, are used to test experiments on the hydration of concrete in zero gravity. It's very likely that we will have an experiment similar on the lunar surface to check the reference material on Earth for building. And you want to compare that with similar binder-based materials for the moon on the space station, and certainly also with the material that is totally comparable to a rock where we do sintering. And you see this is a quite homogeneous material. Even if you look close, you certainly want to understand the microstructure. So, quick note, why do you want to sinter instead of wasting the precious water on the moon? Well, definitely you want to use the water more for biological systems, feed the astronauts. Sintering creates a stone and has no problems, at least not that many problems on the moon than if you had only a matrix material which has different thermal expansion. And if you can use solar radiation, in the end we can produce more, but here we produce the DLR logo of my employer. And certainly you can do many of the ground-based experiments, because especially for the moon, the distance to the sun is it's basically the same as the moon. Bottom line, to sum that up, with European funding, we could produce nice bricks from lunar regolith simulant, also more of them. We used both the atmospheric sun, and we had some simulation to do that. We did it in air, we did it in vacuum, all of it works. You look at the microstructure. You have many components, you have a high glass content. That means you would like to study that from a materials physics perspective. We were very glad that we have a artificial sun, which allows us to avoid fluctuations that you would not have in space anyway. And you can use regolith up to the strength of concrete. And in addition to building something, you can use it for heat storage, radiation shielding, and such. Okay, that's the basis for then constructing things like these. Now I want to come to more fundamental granular aspects. Granular media can be treated as the equivalent of molecules even, and you add that particles are dissipating energy if they collide, and then you're immediately in a realm of counterintuitive effects, like I show here. This is 100 glass beads. They are vibrated from underneath on Earth. And if I lower and lower the energy input from underneath, which is the equivalent of cooling the material, something quite fancy is happening because all the particles are landing on one side. It's a clustering effect. You also have instrumental for some stages of planetary formation. And it's definitely different from an equilibrium gas that would cool and not cluster in a certain region, except for at some later point condensing into a liquid droplet. Doing that in space, here is a granular gas made out of a couple thousand particles on a sounding rocket flight. We can also study cooling. This is how basically the ideal gas law needs to be modified. And red is the theory and black is what we can do in a space experiment. So that matches up very well. You can also look at later stages where you have clustering, but before that, what you see is the unfamiliar non-Maxwell-Boltzmann distribution of the particles. And in that sense, we are following up on recent theoretical developments and try to have that confirmed or disproved or details clarified in microgravity experiments as much as possible. Now, so one application is to use granular materials in the gaseous state as dampers. It's one of the first experiments on board the International Space Station that actually does more than just a mechanical test of a 3D printed thing. So we have a couple of particles in a container and we measure the damping properties of that containers when you put in a certain amount and various amounts of granular particles. So this is an application specifically for low gravity where you can use knowledge from granular gases as a damping mechanism. Here is another one. The blue things you see is a DM simulation of a discrete element modeling simulation, basically molecular dynamics of a fluidized bed. Fluidized bed means I blow some gas from underneath. If I try to do oxygen extraction on the moon, maybe I use hydrogen. And certainly I want to understand the processes and understand the differences from a 1G to a 6G to an almost 0G environment. There's hydrodynamic instabilities and certainly a dependence on the gravity level, but also a dependence on the regolith you're using. So in that sense, we are trying to do the best for the numerical modeling with input from experiments and then cross checks in lower gravity. So you can use a centrifuge on the space station to do things like that. Coming to yet some higher densities, when you can no longer look through. This is the field of granular fluids, I would call it. So it's still not totally motionless. You either have it flowing in front of your eyes or you make it flow to test it. And a traditional view of granular rheology is shown here, where you use sort of the static angle of repose or a dynamic angle of repose. That's a rotating drum to find out about the rheology. One of the first out of Earth rheological measurements was by Buzz Aldrin on the 1969 landing. He deliberately made a footprint, took a photograph, and the rheology, if you like, the proxy measurement, revealed that the lunar soil is quite cohesive. So the goal from our side is to go beyond those empirical laws, because the empirical laws most likely may fail if you go to a different gravity environment, and provide rigid foundations for a granular rheology to be applicable in space applications. Now, I admit the next couple of slides may go by a little quick, but I want to argue in principle that you should read the papers and get back to me if you want more details. Bottom line, if I focus in the sense of time on the right-hand side, you can have a material, you can pick a certain density that's probably looser on an asteroid than on the moon. You can have a shear rate on the horizontal axis, and then you can at least determine a Newtonian, a shear thinning and a shear thickening regime. And the mathematical details I'm happy to explain, but we don't want to spend the rest of the day here. I can change that for different dissipation. That's the epsilon. So we have a microscopic prediction what happens when you take soil. We have not yet the calculations for different shapes of particles, but that in principle can all be done. For the experts in the audience that know the Bagnold law, it's a very peculiar quadratic law in rheology. This can be explained microscopically by our derivations. And if I take a fancy novel rheometer, I can confirm with the shear rate that the stress is quite nicely on top of the data. So the data are the individual dots, and the theory is the colored flow curves here. And this works very nicely. So we're optimistic that we're also able to do more refined problems. You can, if you know the mu of I rheology that engineers in granular research use on ground, you can capture that. And sort of as a summary, we are conforming with experiments. We have a prediction of rheological regimes, and we can capture the most successful empirical laws. And in a sense of fulfilling the motto of making granular materials predictable, here is a first large-scale simulation based upon our calculations, where we simply have a Couette cell, we shear, and we look for the stress distribution or velocities that we have in the material. Can use that model to invent additional processes and mechanisms you want to do. I'm always happy if somebody calls me that some of their asteroid mining processes fail because of the material going basically in the equivalent of suspension. Here we have a vibration pumping mechanism that is intended for lunar applications. So you stick in a tube and you pull out some particles, and due to friction here, you can pull it out and put it somewhere. Here is a student setup for that. And that can be supported by calculation. This is what I wanted to show you here. And with that, I want to already come to a summary. So experiments in microgravity can lay the ground for some basic laws in the physics of regolith that we may need to do predictions and some control. Theory and numerical simulation are good guides and support to the development of applications. So that is what can come in here. And the rheology for the little bit denser materials, also for the completely solid material that I didn't touch upon in detail here. The rheology of such granular media from first principle promises to be predictive enough that for the moon or other unknown environments, you can rapidly map out some parameter space, reproducing empirical laws, showing their limits, and making the prediction of the mission then safe. And with that, I thank you for your attention. And I hope I have been able to give you some nice perspectives of a field that's a little further away from asteroids. Thank you very much.